Okay, let's look at another domain. So suppose I'm trying to classify music, right? Maybe I want to build something that separates, say, classical music from electronic music, right? If I just take a classical recording and an electronic recording, just look at the waveform. That's what a waveform for classical would look like. That's what a waveform electronic would look like. And of course, they're all horribly squished. So how can we go about building a representation? How can we go about building attributes, and what values should we assign to those attributes? Now, if we zoom in on any portion in these waveforms, what we'll see is we'll see a time series, right? Where on the x-axis you have time, and on the y-axis you have amplitude, right? Amplitude, it's kind of like a measure of volume at this instant in time, how loud the music is at this particular instant. So that's what the time series look like. And a simple, naive representation of this would be to just take the data as it comes in, right? What it comes in as is, it comes in as a time series, so you have discrete time intervals, little steps in time, and at each one of those steps, you have a value of the amplitude. So what would happen if we take those amplitude values as our attributes? So basically we're going to have an attribute for each point in time, and the value of that attribute is going to be the amplitude of music at that instant. Right? So that's what I'm talking about, really. So taking that point and saying, okay, that's the value of x1, that's the value of x2, that's the value of x3, that's the value of x4, and so on and so forth. Is that a good representation? No. Why? Exactly. It's vulnerable to the same problem that we have with the words. So if I take the signal and I shift it by a fraction of a second, so just, chop off a millisecond in the beginning, all of the values would change. x1 would have a different value and x2 would have a different value. And that's something that you don't want to happen. Another thing that you could do quite easily is if you just increase the volume. So scale up the time series, all the values would be different. And there's all sorts of other transformations that you could do that would make the representations very different. So how do you represent music? Again, there's lots and lots of ways of doing it. One possible, very simple sort of, if you had half an hour to do it, what you could do is you could say, well, so music is a time series, but it's a particular kind of a time series. It's periodic. Right? And for periodic time series, what we know is every periodic time series, you can represent it as a mixture, as a sum of your basic frequencies. So whenever I have a single signal like that, what I can do is there's a bunch of sine waves, and if I add them up with the right weights, I'll be able to reproduce that time series. And these sine waves, so some of them will have sort of low frequencies, some of them would have very high frequencies. These are called base frequencies. And you have a tool called the Fourier transform that allows you to decompose any time series into a mixture of these. Basically, what the Fourier will say is how much of this sine wave do you have to add to this sine wave to get a signal that looks kind of like the time series that you put in as the input. And it'll give a set of, effectively a set of weights. It tells you to what degree each of the sine waves is present in the piece of music that you're trying to analyze. And then what you could do is you could actually take these weights, the weights for the base frequencies that you've discovered through Fourier, and use them as attributes for representing the music. So, so your attribute would be the amount to which base frequency f is present in your piece of music, and it's nice. It's insensitive to shifts, and it's insensitive to all kinds of volume transformations.